Good morning. We're getting started maybe a minute late by my clock on my computer here. There's some people that are out sick today. They messaged me last night, or they have a family member that's got to be taken to a doctor. So that's going to reduce the size. I wanted to continue the discussion that we started last week about when we're going to have the first exam. And I definitely spent a lot of time over the weekend not grading papers because I was working on getting stuff all pushed out there. Old exams, old quizzes, prepping for the new chapter notes and the new chapter Jupyter Notebook, stuff that has been mothballed since 2020. So that stuff's all rolling, and some other little demos I'm going to do today. We had proposed that we would have the exam on the 3rd or the 10th. I can still go with either, but I'm starting to fade on the idea of the 3rd. I realize a couple people had said last week that the 3rd was better than the 10th. I do realize after looking at the old exams, though, that I've always covered, now I've come to realize I've always covered a little bit of Chapter 3 onto the first exam. And those are in the example exam. So I can still modify it and just restrict it to Chapter 2, but I asked people last night when they messaged me saying they weren't going to come to class, saying, how do you feel about the 3rd or the 10th? And I figured I would get inputs now from everybody else that's here, which is 2, 4, 6, less than half. How do you guys feel about it? Because I'm feeling a little bit more rushed. I can still do it. How do you feel about it? The materials are all up there. I spent all this effort because I wanted to get it up there. The fact that I haven't graded papers is probably disappointing to you, but to me it's kind of like the last thing I have to do because I got to get the stuff out there. You've got the solutions, you've got your paper, I have your paper, a copy of it, and I will endeavor, of course, to work on that now that I've cleared a lot of this overhead away. We're also launching a new lab today, too, so I'm going to spend some time just keeping you up to date on that. And hey, all of you that are here right now are in the lab, so that'll be a good thing, I think, to get. We're perfectly synced right now. We're just perfect alignment for where the lecture is at and where the lab is starting today. I also tested all of the links for the lab, too, and all that material is there. There was problems last week that I didn't realize until somebody told me about it. Why, I don't know, but if something's not right, message me, definitely, because and everybody can benefit from that.
I think the 10th would probably be better.
Okay.
We have more time to prepare.
Okay. Okay.
You're talking about Lab 3, right? Lab 3?
Yeah, exactly. Yeah, the first comm theory lab, which is the rest of the semester now, and lecture is going to be the comm theory side of it too. We've been getting ready for it, and the spectral analysis is important. So Sam, who generally sits right up here, was an advocate of the 10th, of the 3rd, because he has reserve duty or something, but I don't know. I did this for so many years. It's like there's always something, right? There's going to be a constraint, and if I have to figure out how to give an exam in another location, those of you that might be taking it at the testing center, that'll all work out too, because I'll push it over there, and then our plan is still going to be the same. So that gives me a little bit of breathing space that we will delay till the 10th. And you're walking in late, Sam, but it's just the feeling. Yeah. It's just seemingly better at this point. And if there's other issues, we'll work those through. So that means I don't have to dash into making sure I review the old exams, which have been up there since Saturday night, but I can still look at them and still take questions. So remember I said it was a benevolent dictatorship, so no matter what you guys vote for, I still get to decide what makes the most sense. I've also been crazily busy. If you lived in a house for a long time, like 40 years, my wife and I, it's our 40th anniversary year, we're doing a remodel. We're moving out of the house at this weekend. We're moving into a rental home on Sunday afternoon, and it's just a mess. I mean, there's boxes everywhere, and my son keeps telling me, who lives with us, he said, you can't, it's like eating an elephant. You can't do it all in one bite. You have to take it one bite at a time. So that's kind of what cleaning up, packing, throwing away, sorting, turning our garage into a warehouse for the last 3 weeks. And it's going to continue, and it's going to be a 3-month, we're going to be out of the house for about 3 months. And our contractor, although he's moved materials into the basement for part of the project in the basement, we haven't even signed a contract with him yet, which, you know, it's something worthy of talking about, probably even in anything at the university. What is the traditions of our society? If it's two men making an agreement, we always say it's a gentleman's agreement, and how do you do that usually? It's like a handshake, right? That's kind of our tradition. We're very much impressed by this guy. He's not going to go away. We're definitely not going to go away. Our house is kind of all ripped down and everything. So I'm confident it's going to happen. It's just that you feel a little bit better when you sign a document, but it still comes down to an agreement, a verbal handshake, whatever. So before we get into the lecture, I'll just point out what is up there. As of last night, I got the Jupyter Notebook revamped. We'll be looking at that today. There's a PDF rendering. It will probably have some tweaks as we go along the way. A few days back, I reposted the Chapter 2 Jupyter Notebook and rendering because I wanted to clean up some bad writing relating to one of the homework problems that you now have assigned. And we're going to go through that early on here in the lecture too. So there's all kinds of things that I'm wanting you to play with. Hopefully you don't feel like you're lacking for toys to play with when you work on this class, because I do want to keep you sort of multifaceted. I mean, it's what I do in my work. I got another task thrown at me yesterday in my job at ARCA, and I'm working with another engineer who's a modem engineer, and they have to deliver a project, and they're having an issue meeting something, some new requirement that wasn't in place. And I'm looking at code with them and looking at where is the proper place to do some calculation that the customer wants to see in the interface for their box that they're buying. And it's just like what we do in here. We're not just working on one thing. We might go write some code, we might test it, and it's kind of exciting. It's exciting to me because it's like there's always something to do, and if we didn't have something to do for our customers or in learning at the university, what would you be doing? I don't know. Do you have any idea? You might just be working in the services industries, which would be, to me, like consumer services, retail, etc. My son's getting married also in a few more weeks, in the middle of April. That's kind of a busy time, but his fiance is wanting all these other things to do and making income for herself. She decided to go back to work in retail, which she's done apparently many times throughout her life, but you always can do that if you want to, right? But none of you plan to do that, but I bet some of you have been doing that already. You know, things you don't want to do. So I'm going to jump back into finishing off a couple things in Chapter 2. The other things that are in here, like I mentioned, would be the sample quizzes. These are just quizzes that are raw, they're blank. We won't officially be going through a review because we've made this decision, or I'm settling on it now, of the 10th. These two are the old exams, and they are with keys on them, so you have to use the password to get into them. But let's just take a quick look at this, just to give you an idea of what I think you should be able to do with this. because they are blank means that you can go ahead and just write on your tablet. You can print them and write on them. They were used as quizzes in 2020. And what I'm going to throw out there as a possibility, there's a very strong possibility that one or two of these problems, the typical quiz had two parts to it, so 2 problems per quiz. But these or close variations of these could show up on your exam. So does that give you an incentive to say I should be looking at these and working them through? If in desperation you're saying I just don't know what to do with this, we can talk about it in class. So this is an extra assignment to run in parallel before next week to say look at the quizzes. The old exams have the solutions already, and the flavor of those problems are just like these quizzes because they were all done in that fashion. So I think you got a lot of different things to do. I mean, look at this problem. This was the last thing we did last Tuesday. We were looking at distortion in filters, and this question pertains to amplitude and phase distortion and group delay distortion. So we have a plot of group delay and a plot of frequency response. What would be the answer to that problem? He would explain it and say, well, look at the passband of the amplitude response. It's flat from approximately 0 to 50 hertz, and the group delay is flat approximately to 0 to 30 hertz. So if you were looking to have distortion-free transmission through this filter, what would the answer be? Where both are flat. So the amplitude has a wider flat spot. Group delay starts peaking up near the edge, which is a characteristic of most passive filters made with lumped elements and things. You would have to say 30 hertz, right? Because it's good in both group delay and amplitude more than covers that. So okay, back away from that. So let's jump back to where we were in the lectures. We were looking at filters, and I kind of skimmed over, classical filters like Butterworth, Chebyshev, Bessel filters, elliptical, and so on, because what it comes down to in a comlink today is either it's going to be all in DSP, but there's still going to be analog filters somewhere in the chain. And from a modeling standpoint, we're mostly going to be modeling using discrete time processing because that's what we do on the computer. However, I am exposing you into the one homework problem and using scipy.signal to design an analog filter, and that's one of the problems. It's kind of mundane. There's an example of doing that right in the Jupyter Notebook for Chapter 2. This is just the list of the different types of filters that you would encounter on the analog side of things, and right now it's get the right guy selected here. Those of you taking the lab, this is what you were exposed to, lumped element filters, and they will be playing a role in labs throughout the rest of the semester for those of you taking the lab. We also have examples of ceramic filters in lab number 4 coming up. And in terms of what we have in our devices, I think I talked about this last week. We might have crystal filters. We have surface acoustic wave filters in cell phones. And then for other microwave applications, they might be made out of transmission line elements, stubs, open and short circuit, 3 lines. And then for high power, lower loss, satellite communications, it's frequently some sort of a cavity filter made with machined and plated metal. And then it's tuned with tuning elements threaded into part of the cavity to alter the volume or the space to tune it slightly. And these things are not the type of things that you would carry around in your back pocket in your cell phone. They're big and bulky, but on a satellite, you want high performance, and the weight can be more. It's certainly got to be watched, but we still have this variety of filter types. And active filters, I'm sure you were exposed to those in electronics. Didn't you build a Sallen key somewhere along the line, right? They have an S-domain representation. So what I put in the notes, and I had a couple of helper functions like this freq-z response, and then I think the next one down here is freq-s response. So you're going to be using freq-s response in the homework problem. It gets the frequency response from the S-domain polynomial for the filter, the ratio of two polynomials, numerator and denominator. These two functions were kind of precursors to things that I had written in Python, quite a while back, and then they got incorporated. Some of them got incorporated into two modules of code, which are now in Jupyter, so now in scikit-dsp-com. So you're going to be playing with the older stuff in the homework problem, just to carry you through the motions of doing a bandpass filter in this case. And then we'll mostly be doing things with low-pass filters, because when we do things in DSP to implement a modem, we generally have the bandpass filters out in the analog domain, and then inside of our digital signal processing domain, we have mostly low-pass filters because we're doing things in the so-called complex baseband. So it's a complex signal, and we just do everything with a low-pass filter and can move things around and then push it out onto a carrier. So it's not such a simple matter, but what I've pondered about, I spent a long time thinking about what to give you for the homework, and that took a lot of time too. And I said, yeah, let's just look at some analog filters and how you can do them. You saw them in MATLAB, and now you can see them in Python, and scipy.signal has got the filter designs in it. My package, scikit-dsp-com, has two modules for doing filter design, but restricted to just digital filter design. And they're very sufficient for my purposes for modeling and simulation, and that's pretty much where I see things going for the rest of the semester with your projects and things. So you will probably want to use the ones in scikit-dsp-com, which I'm going to demo here as well. When you do need to model an analog filter, whether it be a transmission line element filter or a cavity filter or something, what I've done when the need has arisen, and it has arisen, every now and then. It happened maybe a couple of years ago on a project that I was working on for a 5G cellular base station. They sent me the S parameters from a microwave filter that some member of the team was designing. They sent those to me, and then I could work them into a Python simulation model and make use of them in that sense. So I'm doing it still in the computer, but I'm getting actual network analyzer measurements. And that's kind of one of the reasons why in the lab you've already done that, and you're going to do a little bit of that characterization in Lab 3 too, characterizing components, and then you'll have a model to use in the computer. I don't know, are you starting to see a theme here? When you come out of this class, you're not the hardware implementer person so much as the system level modeler and doing experiments at the system level. But you cross the lines frequently, and some of you are going to do that throughout your career. You're probably going to pick a line and stay mostly on one side of it. You're going to maybe be an FPGA developer. You're maybe going to write code in C++ as implementations of things that have to run in real time, or you're going to be on the other side, be on the system modeling and analysis side, where you will do the simulation stuff and help support the concepts that will then go on to be handed off to the implementers. I started off on the implementation side and then came back over to be a system modeling person. And most people in industry, that was the way it was, and it seemingly is still that way. I'm kind of, I didn't think it would turn out this way, but it does. It has. So when I started working in industry, I was always suspicious of system simulation people. Back in the day, it was a mainframe computer. We didn't have PCs at that time. So the people that did the modeling worked with pencil and paper and wrote programs that ran on a mainframe computer. Now you're saying, well, that's really old. Yeah, it is, but that's the way it was. I worked in the lab. I did the PCB design, and I did my back-of-the-envelope calculations. I didn't really even use SPICE or anything like that. I just worked from textbooks and standard modeling and equations and things for filter design, etc. And to me, building it and testing in the lab was the whole thing that I wanted to do. I wanted to be a person that was the designer that designed something, did a schematic for it, sent it off to get the PCB design completed, got it back from the assembly with all the components mounted on it, and then I started testing it in the lab. And I thought, this is the real deal. But you know, since that time, I've realized there's a lot of energy to go in and a lot of money to be spent making the actual hardware, and building simulation models and testing ideas out is super important in that area. And then some things just plain only run in software. So, you know, times have changed. I go back to thinking about the garage door opener, which was a simple transmitter that just transmitted a carrier with a tone on it, and then the garage door receiver inside your garage or your house would just open the door. Well, those days are really long gone, right? Because what's so bad about that? Somebody can break into your house really easily because it's so simple. So then that's just been an escalation. But so the garage door opener, though, still in my mind is a 9-volt battery, maybe one transistor, some lump element parts, put in a plastic housing with a little loop antenna and a button on it to turn it on and off, you know, press it to transmit. Your key fob took us into that domain too, but those didn't come around initially because key fobs were like electric door locks in your car. Nobody had such a thing as that back when. It was your key that you turned and twisted. So that came after the garage door openers were around. So, and of course, cell phones grew up in that time frame too. I'm kind of rambling on this, but I'm just saying there's a lot of things that have stayed the same and other things that have morphed in an appropriate fashion. So I'm going to let you deal with this homework problem and just work through with the hints and everything that I'll eventually push out to you, but it's very straightforward to just model it according to what I have in the Jupyter Notebook already, and I could jump back over to it, and I could go up to this is a Bessel filter. Let's see, which one are you doing? I'm having you do a Chebyshev type 1, I think. This Bessel is similar. Divided by zero error, not a showstopper necessarily. What I'm looking for is where I had you where I have you design a filter. It's in the assignment sheet. So let's just go look at that. Save some time here. So kind of the key right here is you're going to be using scipy.signal, and you're going to be designing a Chebyshev 1, and this is the important thing. You're designing using the function in scipy.signal that makes it an analog filter, and that means it's going to be coefficients that form h of s, a ratio of polynomials in the s domain, which most of you say that's where I live. I love the s domain. It's my analog hangout, right? I'm on the other side of that, though. I'm into h of z, which would be the digital filter side of it. And I'm going to show you that, and that's what we're going to be playing with mostly from here on out. But this just lets you know that you can design analog filters, but when you get these coefficients over here, what are you going to do with them? I mean, you have to synthesize that into an actual analog circuit design. And that's, those of you taking the lab got to see how you can do that from the parameters for Chebyshev and Butterworth and so on. So I'd rather have the digital coefficients because I know how to implement it with a difference equation in simulation, and it can run in real time too. But at any rate, this is just part of that question. The other problem that's in here that I'm going to now switch over and look at for a little bit is spectral containment bandwidth. And this comes to mind because it shows up frequently in what you do in digital communications, but I also saw it when I was grading a paper last week with that root raised cosine filter model. Somebody said, oh, we want the 3 dB bandwidth, and that got burned into your brain a long time ago, right? You see a filter, you want to know where the 3 dB cutoff is. Maybe, maybe not. So this problem is going to turn things around for us, and I'm now going to go off and look at it. And then I'll come back and give a tour of the filter design. So what I have hidden up above here, and this is based on problem 255, which I've given you to work on, is spectral containment bandwidth. And this is written from the standpoint of an energy spectral density, but energy spectral densities and power spectral densities behave similarly in terms of what you do with them. You can calculate the amount of power in a band of frequencies or the amount of energy in a band of frequencies. And if it's a random signal, then energy spectral density actually seems more appropriate just because of the fact that it'll be aperiodic. The autocorrelation function, thinking back to when we've been looking at that. So the idea here with the fractional bandwidth or spectral containment bandwidth is we assume we have a low-pass type spectrum in this case, and that's what this problem deals with exclusively. So it'd be a baseband kind of waveform for communications, signaling of some sort. So what we want to do is we want to say, going from DC up to some frequency, in this case it says B90, and B90 means where we have contained 90% of the bandwidth, or 90% of the energy, or it could be the power if it was power spectral density. So we'd be integrating from minus B90 to plus B90, but due to symmetry, it's going to be 2 times 0 to B90. The 2's cancel out in the problem. And then it just becomes at the end this ratio where the bottom is the total energy or total power, and the top is a fractional amount. So how do we do this? This looks like it's a numerical integration problem, and it certainly is, but we can do this, or an integration problem, but we can do it numerically on the computer very, very easily. And that's what this example in the notebook is all about. So just turn that away. So I said this is what it boils down to, is this calculation here. And how are we going to do it? I'm suggesting you can do it from problem 255. A couple of the parts you could actually integrate. So you can do it according to this ratio of the integrals here. In the general setting where you can't integrate it easily, maybe going to look up tables for integrals and things, you can always just model it and then numerically integrate it. And you can choose the partitions in the numerical integral to be really tiny, and then you get very good results. So this is a waveform shape that we looked at earlier without me saying any words here, but it's on my mind. Remember what this looks like, especially those of you that were in the lab. This is a pulse that's up for half of tau, and then it's down. So it's a full width of tau, but it's shifted back and forth. So it was the Manchester pulse. So it's half up and half down. So, and this was used as a type of line code. We talked about it in class, and people were playing with this last Tuesday in the lab. I'm specifically looking at people. I remember looking at your instruments, and you were putting the Manchester code through a ARB function. I think you had to use a CSV file to create the ARB pulse, right, for this. So we can go to our Fourier analysis, and we have exactly the frequency response. We can get the energy spectral density by just squaring that. So there's our G of F. And then we can just numerically integrate this. So we can amount to calculating this through a numerical integration process. And it's really very easy to do that because we can just use the function that you saw in MATLAB and also is in NumPy, cumulative sum. So cumulative sum is kind of the answer that we're looking for. It will take the elements that are in G of n and accumulate them starting at the beginning of the array, and it just keeps adding onto itself. And it's a non-negative quantity, so it gets bigger and bigger as it goes to the end of the array. And if we divide by the sum over that array, that's basically doing the lower part of this expression, integrating over the entire interval. And this will be integrating it as a function of the upper limit, which will be the frequency step size as it moves along. Now, what has to be done here and what has to be done when you work this homework problem is you want to make it flexible. You don't want to have to say, I have to have tau if I'm going to get myself an answer. Instead, you want to look at the expression and say, can I create what's called a normalized version of the function? And then I can combine f and tau together and work in a normalized domain. I'm trying to think what was an example that maybe you had in electronics or something, like a time bandwidth product or something for some circuit design. So what you can do here is we say combine f and tau together and call that fn, a normalized quantity, which is the product, normalized frequency variable, which is the product of f and tau. And then I can just throw that into the integral up above. And then I can work the numbers back out again by, once I have tau, I can take an exact value of tau, and then I can get the exact value of frequency in the bandwidth. So here I'm just going to do that. Here's the function plotted, the g of n function, and I'm just sweeping fn, which is f times tau, as my variable. And it's normalized frequency, so normalized by 1 over tau is the way of thinking of it. 1 over tau would be a frequency, right? So I'm just f over f tau, if I wanted to call it that. F tau could be 1 over tau, and then this would be a normalized value, like in the pulse train, for example. So this would be 2, 1 over f tau, 1 over tau, 4 over tau, as we're sweeping out here. So as we go out higher and higher, we're eventually going to accumulate. The cumulative sum is going to run across this. So all we have to do is just form the cumulative sum and then get the total through the sum and then just plot those two. So this is what we get, fractional power containment, and it's giving you the intended idea that when you start at 0, there's nothing contained, but as you start integrating out further and further, eventually you approach 1. You're totally contained in that bandwidth. But it's asymptotically approaching 1, so what we're interested in is what value along this axis do we cross 0.9? Is that making sense? Where we've captured 90%. It could be 85% in a requirement. It could be 95%. I worked on a system once where they wanted the 99% containment bandwidth. So the definitions can come differently depending upon how somebody wants to specify it. So in this problem, it's the 90% bandwidth. So how do we find that? We did this numerically, so we don't have all the values to correspond. In other words, what we want to be able to do is map from the y-axis back to the x-axis. So how can we do that? It's sort of a, I'll say, a cheesier way of doing it. We just make sure we have find steps in tau or f tau, and then we can do something that in MATLAB, I'm sure you all got exposed to the find function. Just say find based on some condition of the elements in an array, find the condition where this is true. Python doesn't have it. It has this line of code that I put in here. You have to use the ravel function based on a condition as an argument to the condition, or the condition has got inside of it what you're trying to optimize or find, and then you find all the non-zero values. You can look this up, but I sort of have this committed to memory. When I first started using Python over 10 years ago, I was reaching for the find function in Python and it wasn't there. I had to figure out, how do I do this? Well, they have the capability in the language, they just have it a little bit wrapped up. So I just wrote this little helper function, find, my find, based on a condition. So how do you use my find? You say, you put as an argument inside of it the absolute value of this array, which is going to be cumulative sum over this constant G total, and you want to find the zero crossing. So you subtract from that 0.9, that's to find the 90% point, and then you want to find the elements in the array where this is less than some tiny value. In other words, you're homing in on the zero crossing. You're going to home in. You're basically looking for something, 90% is right in here. So you're trying to find some of the points that are close to that 0.9. Does that sound believable? I mean, in the olden days, you would get your ruler out after you plotted the function. You could just draw lines on it and say, I have it accurate to within my pencil letters width or something. That seems pretty crude today, though, right? So this is root finding, is what it's also known as. So we put that value in, and here I run it, and I think I ran this last night, so let's see. Yeah, it's giving me the answer. So it's giving me an answer, and it's giving me 3 indices is what it's giving. So it's find my index. So find my index on the y-axis value, what indices corresponding to y-axis values satisfy this condition. And then as soon as I find the index on the y-axis, that index corresponds to a value on the x-axis through the original fn value over here. So then I just punch that index into that fn array, and I have what I'm looking for. But here I picked 0.0003, which is a pretty small value, and I get nothing. Suppose I put this at 0.001, it's getting me just 1 value at that point. If I try to home in and I don't have sample points, enough sample points, what can you visualize right now might happen? I'm searching, I'm trying to find a pinpoint, but I don't have enough points along the x-axis that I use to create the y values with, and I say I want to find this value, and I don't actually have a value close enough. So what's it going to return? What might it return? Nothing, right? It'll fail. It's like you're asking for something that doesn't exist. There's no point on the y-axis that's close to 0.9. Here it worked. So don't, when you're doing this on any of the problems, don't make this value so small that you'll get just an empty array. You'll have a no for an answer, and you have to interpret that, right? this is always the problem of being in class early in the morning or anytime when you first wake up, is your brain just always raring to go. You look at something and you stare at it and you say, what am I doing? I mean, has anybody ever had that problem? It pretty much happens all the time. Late at night, same problem happens, right? You're shutting down and you're not being able to coherently do work. But at any rate, still, it looks like 1448 is good, so I plug that number in, and I'm just using an F-type format in the print statement, and it's giving me 1.45 hertz second, because that is the units of Fn. It was frequency times seconds. So now we can solve for the value in hertz, though, if we know what tau is. Say it's a Manchester pulse, and tau is, I didn't do this right. I still have to think about this because now I maybe still don't have it right. I think it's still tau over 2. At any rate, this is just an example. The problems you're working are different from this one. But the idea is we can go back, and if we know what tau is, then we can take and apply tau to get the 90% bandwidth, because we're getting an answer in terms of F times tau, so we just divide that number by tau, and now we get an actual value in hertz. So in this case, if I said tau was t, which is 1 over the bit rate, then I can spin that around and I can say, oh, I'm at 1.45 times the bit rate. And I would see that from here because I'm looking down, and yeah, there's 1.45. That's about where the 90% is. Is this making sense? And if your customer says, I want you to go to 95%, all you'd have to do at this point is you just put in 95 up here. And now we can see that when you get out at 95, it's so flat out here, we can take this number down really tiny and probably find, yeah, 2454. So it's 2.45. And if you had to go to 99%, that's going to be up in here somewhere, and we can search for that value. Now this probably seems pretty crude. We can make this more sophisticated. There's root solving libraries in SciPy itself. We could find it very precisely and very simplistically. But I think this more hands-on approach seems like we're just moving up in sophistication from getting out a ruler and drawing lines on a plot. We're kind of being more diplomatic about it and getting at it. And yet you have a hands-on feel about what you're doing. You're just not punching into something and saying, there's my answer. Because you can go look at this picture and say, what do I expect? I expect it's going to be, at 0.9, it's going to drop down somewhere in there, and I could zoom in on that even too. Everybody good on this idea? When the going gets tough, the tough gets going is one good statement. And then yesterday in my meeting with this guy that I got acquainted with, they don't have any money to add this feature, and they have to deliver the product. They don't have any money to even have them talk to me because I have a billable hour rate through the company. I said, so we have to get something that meets the requirement, and it probably should be, we should probably be considering the use of the KISS principle, which is keep it simple, stupid, right? If you haven't learned that term, just get used to it. Your boss will say, we want this, but we don't want you to spend any time on it. We want you to get this figured out with almost no time and just meet the requirements. So I'm excited to see. I may be meeting with him this afternoon because I was trying to point him in the right direction. Okay, so that will take care of that problem. What I wanted to do is, and now I'm in the EMO notebook, the reactive notebook, and I just decided I would give you a quick tour of how digital filter design will work, and it's either now or later, and I decided I would do it now. If it comes up in a project where you have to design some digital filters, and I want you to play around with filters, I'd like to have you just use what's in Scikit DSP-Com. And if you go over to Scikit DSP-Com's documentation, there's two modules in here, FIR Design Helper and IIR Design Helper. So the IIR Design Helper designs the classical digital filters from analog prototypes. Like we'll do things from Butterworth, Bessel, Chebyshev 1 and 2, and elliptical. This is built on top of what's in SciPy.signal. I didn't create anything new. I just remapped it and created an interface that was to my liking. It requires things like passband, stop band, ripple in the passband, attenuation at the stop band, and a sampling type in all of these types. And then it has some other helper functions for doing frequency response, cascading, doing second order sections. If you're doing a real-time implementation, you would want to do what are called second order sections, and it can do a pole and zero plot in the process of getting there. The FIR design, which is far more common in digital communications theory, is what's in here. We have two classes of digital filters that are finite impulse response that are also linear phase, which means they have no group delay distortion. The IIR filters give you a lot of attenuation, roll-off, bang for your buck, but they have an ugly group delay. So they're not used as often for critical signal flows. They might be used in other parts. But the two types that I have in here, which I kind of went off on my own to do using a function in SciPy.signal, namely the function is called Remez, which is the name of an algorithm that was developed many, many years ago. The Remez family of filters, bandpass, bandstop, high pass, low pass, and then Kaiser window-based filters, and then some other helper functions along the way to get things like the filter order. So the advantage of these types of designs that I have in here are you always get the filter order. You say, I'd like to have this bandwidth, I'd like to roll off starting at this response, I'd like to be down so many dB, so many hertz above that, and then it will tell you what order filter it's going to take so you know what the complexity is. So how does all that unfold? I could do this in Jupyter, but I decided I just have this notebook going. This is the one that I put the CAF function in. So what I have to do to make this work, of course, is I have to import FIR Design Helper as FIR_H for its short name, and IIR Design Helper. So I have those two imported. And I'm just going to pick a sampling rate of 1 megasample per second. And this would be typically the way you would get into your doing a discrete time simulation. You would assume a sampling rate, and you know you have from 0 to fs/2 to work with from sampling theory, right, Nyquist sampling theory. So I'm putting in a 50 kilohertz and a 70 kilohertz for pass and stop band. I want half a dB of ripple in the pass band, and I want a stop band attenuation down 80 dB. So I'm doing two types of designs. One is going to do a Chebyshev type 1, and the other one is going to do an elliptical. And I can always, in the case of Marimo, I can just hover over the variable and it will pop up, the help for the functions. So I wrote these functions to give you the A and the B coefficients, numerator and denominator, but I also give second order sections, which is a way that was built into the DSP, real-time DSP lab. So that's available as well, and it's supported through SciPy.signal as well. So I design it, and the requirement ends up for what I threw at it is a 13th order Chebyshev type 1 is the blue one, and the elliptic filter gets by with considerably less. And I'm thinking you've heard this somewhere, but if you don't remember it, the essence of an elliptic filter is it will get you the amplitude response requirements met, namely the cutoff frequency and then down to the stop band, with the smallest order filter. That's the nature of the elliptical filter. It's very efficient, but it comes at a price. It has really bad group delay, whereas the Chebyshev filter takes more poles to implement it, but it has a nicer group delay, but it's still pretty ugly in another sense. So I'm using, to make this plot, I'm using a function that allows me to put in I'm using the cascade second order sections just for efficiency, but this frequency response list means I can put in a list of filter designs and I can compare all of them right on the same plot, which is kind of a nice tool, and that might factor into one of the projects. I'm not really sure at this point, but it allows you to just compare filters of different types. So I've got different types thrown in here, and then I can control what type of mode it's in, and the mode is whether or not I'm going to display dB magnitude, phase, group delay in samples, or group delay in seconds, all versus frequency. So you get the ability to do some modeling with that. So here's what the group delay looks like for the two filters. The Chebyshev is actually worse than the elliptic filter, but they both, that's far from flat. Notice we were thinking if we wanted to be flat out to 50 kilohertz, we're just not there with this type of design. If I was to put in down here, an X-lim, and go, say, 0, 80 E3, so out to 80 kilohertz. It's not too flat. I mean, we're going out to 50. We definitely have a bad thing going on out here right at the cutoff frequency. It's not too bad in this regime here, but it's still not great. So what would happen in a practical setting if we were doing this in the analog domain? We would have to equalize this filter by putting in delay out in this region to come up and match this delay peak, so we could have a flat group delay out in the passband. Does that make sense? Cavity filters would have these problems, any other types of technology. This happens to be a digital filter model, but it's still representative within some distortion factors of the true analog prototype in the S domain. I know in 3205 you look at filter design. Do you remember bilinear transform filters? Is that something that Dr. Trimboli talks about, bilinear transform?
I think, pretty sure we did in circuits too.
Okay. It has to be a digital filter, though. Now, in electromagnetics, the bilinear transform is also what takes you, is what a Smith chart represents. It goes from impedances to a reflection coefficient. That's a similar type of mapping in complex variables. But at any rate, you can put in delay back in here to backfill this and bring this up, and then you'll have it flatter in the response. And cavity filters can do that to group delay equalize them. So here's what you'll probably be picking from for digital comm stuff is linear phase. So the FIR filter, here's the Remez, and here I've made the response not quite as critical as I did up here. I tried to make the cutoff very, very close to the stop band attenuation. It's 50 kilohertz and 100 kilohertz. I don't know, does that impress you as dropping over a very steep waterfall? I mean, it's dropping really fast. I could soften it up tremendously. I mean, I could put in a number here like 100 for both of them. And this is a reactive notebook, remember, so I typed in one cell and the other cell's calculated. So now it pushes out and it's much softer. And the group delay if I rerun it, well, it actually ran right away. It's much more benign looking at this point. It's not too bad actually at this point. So in the FIR filter, because it doesn't have poles except poles at 0, I can't get as much bang for my buck out of this filter. I have to use a lot of taps in the FIR filter. So here I've got 50 kilohertz down to 100 kilohertz for the stop band. The equal ripple is a very efficient design because it's putting an equal ripple into the stop band. And that equal rippling action looks kind of nasty, but it's down at a certain number of dB, in this case 80 dB, so it's pretty acceptable. And whereas the Kaiser window drops off and meets the requirement, but notice the difference in the length. The Kaiser filter takes 101 taps, or order, and the Remez takes only 66. So it's very, very efficient in that regard. And then the group delay for both of them is half the length of the filter. So it's going to be like 33 for the equal ripple and 51 for the Kaiser. But it's flat, no delay distortion. These are beautiful filters. But it takes a lot more math to crunch this out in real time. You have to do all those coefficient multiplies and then additions. So what else could you do with this to make us to sensibly understand, is this filter really working? So I could make a noise sequence. In this case, I'm using Gaussian noise. So I'm using rand n, which is Gaussian distributed random variates. I'm taking 100,000 of them. I'm going to pass them through, and this will be what you'll be doing in projects. You'll be using L-filter, and I already introduced you to L-filter earlier. But L-filter lets me put the coefficients in the numerator, a coefficient of 1 for the denominator because it's an FIR filter, and then I'm going to use the power spectral density calculation just to get the power spectrum of the noise at the input. And I'm using the calibration of noise of true, so that way it reflects for noise at least 0 dB when I'm putting in a unit variance Gaussian variant up there. And then I pass it through the filter, and I see it takes on the shape of the frequency response. And this is just a reflection of this theorem that we talked about last week with power spectral density. The power spectrum of the input times the magnitude squared of the frequency response is the power spectrum of the output. You've seen this in the lab. We'll see this throughout the rest of the semester. It's cool, right? I don't know what you think of it, but the frequency response of a filter is sort of like a sinusoidal theory idea, where it's actually sending a waveform through, and knowing that it's white noise, it's getting shaped or sculpted by the response of the filter, and it's taking on the same quantity, right? It's not perfectly constant, and if I was to use a lot less samples, suppose I just cut this back by 1 order of magnitude, now I don't have as much, and only have 10,000 samples going into the spectral estimator, and it's noisier looking. And if I wanted to do a model to get more precision, I might take it up to 1 million samples, and then it's looking beautiful by my estimation. It's accurately reflecting what I'm expecting to see for that FIR filter. And another thing that I could do, which I'm sort of tempted to maybe not want to do this, but I'm going to do it just one time here. So I could go into Z-plane, and I could pick B of the Remez filter, which was FIR1, and put in 1 in here. And then because I'm in this Marimo notebook, it's not going to display the output until I use plt.gca, a graphics handle. And in this case, there's 0 sitting way out here. It might be an artifact in the rooting of the function. So let's go to the other one just for the fun of it, because there's a bunch of zeros sitting there in the unit circle. But let's pick the second one and see if that'll give a better looking picture. There. There's what the other filter looks like. This is part of DSP, though, to see that all of the responses are being tied down on the unit circle, which is where the frequency response comes from in the discrete time domain, by those zeros sitting there on the unit circle. And then the passband of the filter is described by the zeros that are sitting either side of the unit circle, closer to the origin, closer to 1, 0, I mean 1 at an angle of 0. And that's characteristic behavior that, again, modern DSP teaches you, is that those zeros are occurring as quadruplets. This is in the sense of multiple births, but it's a quadruplet. So we have this 0 has a conjugate 0 down here, and this 0, which is the conjugate reciprocal of this 0, also is sitting down here. So there's a quadruplet of zeros forming the passband. Just to me, it's exciting. To you in comm systems, it's like, oh, okay, I'll go with it. In DSP, it's like a property that you can recognize that. And if we had quantization errors and things, what would happen? It will alter things slightly. You know, if we can't represent the coefficients, here we're representing them with double precision floats, which is just for modeling. It's not going to be that way in practice. Okay, that's enough of that. I think going back over to what I did not go through, pulse resolution, rise time, and bandwidth. Not super interested in this, but it is something that you've seen in electronics before too. It's just telling you there is a relationship between the width of a pulse and its bandwidth in hertz. So the book develops a simple model based on a bounding idea for Fourier transforms. And what it's saying is that in terms of the spectrum of a pulse, you can make the areas equal by choosing an appropriate value of W, and this is kind of like the fractional bandwidth idea. And it just says that you can come up with this relationship that for a pulse of width t, the bandwidth is 1 over 2t. So we have this reciprocal spreading idea. Just saying if the pulse width is t, 1 over 2t is less than or equal to the W. The problem with this is a bound, and it doesn't work very accurately. So for some signals, it will do better than others, but I'm not really going to dwell on this. I'm not going to ask you questions on it. I did not assign any homework problems on this. Likewise, we have things that you learn about in electronics. Rise time, going from 10 to 90% is kind of the standard. And I don't know, many, many years ago when I was in electronics, this is what I committed to memory. And I'm willing to bet you still see this in electronics too, maybe. You still see rise time, the 0.35 over the 3 dB bandwidth of an RC low-pass filter. This is still an interesting, useful metric. It's just something that harkens back to analog design. And then there's other things that go along with it. The rest of what's in this chapter, though, is sampling theory, which we will get to when we need it in Chapter 3. And the Hilbert transform will be integrated in the Chapter 3. And the discrete Fourier transform and FFT, I don't know, you've seen them before, so I'm not really reviewing them. We've been using them all along, and everything we do uses an FFT to do calculations. Everything we were just looking at today with the filters has an FFT hidden down inside of it. So I'm ready to jump on into Chapter 3. Any questions before we wrap up? I mean, what I will do in the review next week is I will talk about, where we're going to draw the line on the exam. I will be making an assignment, but I'm tempted to say it's not going to be part of the first exam. You know, if I don't give you any problems, how can I be testing you on them? I think that's only fair. Even though I haven't graded them, at least you've worked them and you've seen the solutions, but that's just the way I'm thinking right now. But we do want to get started with linear modulation theory. We do want to also compare that to what the lab is starting with today, and the lab is starting with mixers and amplitude modulation. So this topic in here in the lab is identical to, it's tracking right with what we're going to be doing in the lecture right now. So the things that this chapter has inside of it is double sideband modulation, amplitude modulation. I'll mention single sideband, vestigial sideband. They're not all that common anymore. They are used in certain commercial and amateur radio uses single sideband. It might factor into a project though, just because I've done this in the past. Vestigial sideband was very popular in analog television, but it shows up in HD TV broadcasting as well, and I'll at least talk about what vestigial sideband is. A big topic though is frequency translation and mixing. This is a huge, very simple idea, and it's one that's very important in communication systems modeling. It's not the rocket science type of calculations that you may be expecting to see, but it's mundane, but yet it's very, very important. And this is integrated into the lab in a big way. A little bit on interference, and then we'll quickly review sampling theory, bandpass sampling, and then look at modulation schemes that have been used for pulse amplitude modulation in its family is sitting out there, and then delta modulation and PCM. So probably the one that I feel like is in most of our lives more often than not is PCM. When you listen to a compact disc, which you may or may not do, you probably don't do that anymore either, but if you buy a CD, you're listening to PCM digital audio. If you like playing with robots and motors and robots, they're using pulse width modulation. So they're kind of off to the side. Multiplexing is thrown down here at the end too. A lot of this stuff, though, transformed into the digital modulation that we are now relying on heavily, but the roots are still back in the fundamentals here. And one of the guys I worked with at ARCA said, "Are you still going to teach them amplitude modulation?" And I said, yes, because it's one of the foundations. It's legacy. I mean, legacy is legacy, right? Do you know what I mean when I say legacy? It's all over where we live and what we do. I mean, we have legacy, this and that. So if you are talking to a more senior person, you need to know the legacies and things of how this came into being. So getting on with it, before we take our break here, we want to take our message signal, and this is the book's notion. They use the term message, and that even seems old-fashioned. It's like, message, what is my message? Well, probably what I think of, since I was doing a lot of backcountry stuff in scouting, a message might be SOS, right? Just simply, I'm in trouble, I need help, so I'm going to send a very simple message, SOS. But a message could be speech, music, it can be digital data. You know, it's all the things that we would send from point A to point B. And typically, if we're doing RF, radio frequency communications, we're going to locate it on a new frequency so it can be efficiently transmitted. So the message is going to be carried by a sinusoidal carrier in most instances, because why would we carry it on a square wave or something that has all these harmonics? We'd be hogging lots of bandwidth. But there might be an application where maybe you want to do that, but most of the time, almost all the time, we're going to be using a sinusoidal carrier. So we have this that we looked at the very first day of class, and our focus is amplitude modulation, or linear modulation as it's called in the book. This is what we're focusing on. The phase modulation term, which is sitting over here, right now is something we're not going to dwell upon. However, we are going to look at that as being something that might be an unknown or a perturbation factor in making things hard for the linear modulation to function. In chapter 4, the focus is on phi of t being what we apply to carry the message signal. But we still always have something in the phase, or the argument of the cosine, that's going to be phase noise, or some artifact, or some uncertainty that we might have. So when it comes to the analog modulation then, or linear modulation, we're mostly interested in A of t and fc, and then we'll have as a parameter phi of t. So this does enter in, because it's an unknown right now. Simplest form, we set phi of t equal to 0 because we're not putting modulation on it. It'll just be an unknown that'll affect some of the schemes for demodulating. But we're just taking A of t times cosine 2 pi fc, and A of t is placed in one-to-one correspondence with a message. It might be the message directly. It might be a message with a bias on it. Something might be happening there. So this constitutes what's called, in the beginning here, it's just called double sideband modulation. And this is old-fashioned also to say, what is double sideband modulation? It just simply says is that we have an upper sideband and a lower sideband. It's not the fact that we have it shifted up in frequency and shifted down in frequency from the modulation theorem, but instead it's this idea when we shift it up, we have a band of frequencies that gets occupied by the message sitting above FC, and then we have another band of frequencies that gets occupied by the message on the lower side. So we have the lower and upper sideband. But we have this knowledge already, so nothing new here. We discussed the Fourier transform. If you look at our message, it's some signal of some sort, speech, digital information, whatever. And what happens when we multiply by the carrier, we get this filled in waveform. So it has an envelope that's the red, that's switching in sign because the sine and cosine changes polarity, and then it's filled in with carrier on the inside. So when you look on an oscilloscope or on a waveform or generator, or from the generated waveform in the lab, let's say, you're going to see it filled in. And if you zoom way in, you'll see the carrier cycles. So this triangle shape is just a generic placeholder shape for the spectrum. It's used in most textbooks, so I'm using it here. It's just a reference shape. Now we might say that the bandwidth is W, so we're going from minus to plus W. So we're transmitting that waveform, and now the communications link is so simple. All we're going to do is say we're going to go over a channel, which is free space, cable, whatever, fiber optic, whatever, we're going to send it over, and we're going to receive it. And how do we get our signal back? And remember I said last week that we're going to be thinking about idealized components. The mixers are going to be idealized in our math modeling here. In the lab, it's going to be the real double balanced mixer or some sort of analog component. And then the low-pass filter, we're going to make an assumption initially that it's an ideal low-pass filter, because right now we're just at a concept level. And this, does anything seem very complicated about this right now? It seems like this is so simple. And this was, what was developed in the first days of radio. This was the fundamental type of radio. But there's a nuance in here which we're going to see almost immediately before the break that makes this not so easy. Right now it looks on paper like it's easy, but I'll just give you a hint right now. How can we have perfect knowledge of our carrier over at the receive side relative to the transmit side? That blue line that I just drew on the page is like a magic genie waveform, and we're not going to carry that cable around with us and pass it over from one side of the link to the other. So that becomes a major thorn in amplitude modulation, and it becomes a thorn in digital modulation in general, the need for what we call a coherent carrier. But we have to let this unfold. So let's just do what an engineer does when they see a block diagram. We see a block diagram of a concept. We see that we can transmit and get this spectrum. We've moved it off of DC. We can find an allocation that the FCC will give us to send our double sideband signal. Now we want to say, okay, we're sending it through the air, propagating it, receiving it with an antenna across this channel. Now let's test out the idea. Does this block diagram serve as a way of getting back our message? So YD, the textbook's notation, D is the recovered information off of the carrier. And what we do is we just simply go through the math on this. This is what you should be just, I want to work the math. And this is where the trig identities obviously come in. So we have in the square brackets there the signal that we're transmitting, amplitude of the carrier, AC is another unknown. And we're saying in our block diagram, we're going to build in this 2, and that's a mathematical convenience so that the trig identities 1/2 gets canceled out. So when we take cosine times cosine with the 2 in there, we're going to get 1/2 the cosine of the sum and 1/2 the cosine of the difference. So that's for the special case of the frequencies being identical. We get a DC, and then we get a double frequency term. And we're going to be seeing double frequency terms all the time when we're doing demodulation. This should just seem so easy, and it is, but like I said, we're going to explore this more. So when we do that, this is what we're going to see if we were to plot the time domain waveform. It goes from looking like this with the envelope positive and negative. If we use a coherent carrier to demodulate it, we're going to see a time domain waveform that looks like this. And the portion of the waveform that represents this piece right here is causing all those carrier cycles to creep in, but they're staying on the right side of the envelope. It's not two-sided like it was in the transmission side. And it's at twice the frequency. But then we also see blended together because of the superposition, the actual message is inside of that. And if we come along and just put a low-pass filter on it and suppress that double frequency term, now we'll have back the message. That easy. The AC can be dealt with as just an arbitrary scale factor. You can think of that as being part of automatic gain control in a receiver, where they have some gain leveling so that if signals get stronger or weaker, they hold it constant. And that's a feedback control loop on a gain controlled amplifier. And what do I mean by gain controlled? My first project in industry for the optical comm I worked on at White Sands Missile Range was an AGC amplifier that worked with laser pulses coming in through a photomultiplier tube, but I still had a feedback path and a control loop through op amps and things that controlled the gain of the amplifier chain using, of all things, PIN diode, PIN diode, voltage controlled attenuator Now that seems abstract, but you can build a variable gain amplifier, and you can have it be controlled by an analog control signal and or digital. I don't think you've probably had to even think about that, though. Think about an op amp, and you can control that with the resistors, right? But this is going to be an actual controllable gain amplifier for the AGC part. So the only requirement is that the message bandwidth, that the filter bandwidth here be greater than W to not remove any of the message information. And 2FC minus W has to be, that's this point right here, has to be above the cutoff frequency of the filter. And idealized filters is what we're showing here, but it's actually going to be a filter that has a fixed roll-off. And you're going to be, in the lab, you'll be doing things with the filters that are on that RF board. So now, I'm going to jump over to Jupyter for a second, just to let you know where we're headed and do a sound check. So this is what I pushed up there last night before I went to bed, was the updated version of the Chapter 2 Jupyter Notebook. The Chapter 3 notebook. The Chapter 4 still needs to get updated. So you can play with it, but it will have to be updated to the newer conventions of the imports that I want to do. So here I'm adding something new that we're going to get exposed to here after the break. It's another part of the scikit package. It's called multi-rate helper. And what I use the multi-rate helper for is it's a class, as in a Python class. So you can make multi-rate helper objects, and then it has methods that go with it. And this is something that I guess I want to throw out to you. You learn C programming, right? But some of you have taken C++. How many of you have done object-oriented programming? I'm just curious. Okay, so you know the value of objects. Python is object-oriented from the get-go, and you can write your own objects, so, or classes, I mean, and then you can instantiate objects. So that's what I'll be doing here. I'm doing that so that I can make it easier for us to manage multi-rate signal processing, more than one sampling rate, without having to be exposed to all the math of that's part of modern DSP. And the fact that I've said modern DSP or DSP quite a number of times already today, there's like this relationship. COM theory, digital COM, and digital signal processing are just like this. In the olden days, a radio was built using your analog circuit design knowledge exclusively. Now it's pretty much mostly into the digital domain, DSP domain, but analog is still in there. There's nothing about radio systems that is void of analog. It's absolutely there. You can't live without it. So if you're thinking, why did we study all this circuit design? Well, it's still there, and it's something that electrical engineers hold above the other engineering disciplines. You have this broader background because you have to be able to work across the domains, and computer engineers don't have as much knowledge in that area. Electrical engineers have the knowledge. I'm trying to make you can pat yourself on the back and say you're getting a robust degree that has the ability to span over. But object-oriented programming is something that I think is becoming more and more essential. So if you don't know C++, you might pick it up. And you can start by looking at object-oriented programming in Python. It's a very natural flow compared to having to do it in C++ and having the compiler and debugging. But you can do that in Visual Studio Code. As a matter of fact, I was just verifying because I'm using C++ now in my work once again, but I have Windows subsystems for Linux on here, so I was just checking, did I put the compiler tools for C++ in my Ubuntu side of my WSL, and all I had to do was just type G++-V, and this is the version that I'm running on my system right now, version of GCC, which is the GNU compiler collection as it's known, and GCC has the C compiler, and G++ is the C++ compiler. So I don't do this all the time, but I've had to do it on and off over quite a large number of years, and it becomes part of something that you can jump back and forth, not being an expert immediately, but you can get back into it. So here I'm importing packages, and in the zip package for chapter 3, I also have 3 audio files in there, which we'll be playing with quite a bit. So I have a female US audio snippet, a male US audio snippet, and a UK audio snippet. And I just found this collection of audio test vectors out there on the internet quite a long time ago. And so I just did an ls command in Jupyter Notebook. It could be Windows, Linux, Mac OS. ls lists the directory that you're currently pointing inside of, and here's those 3 files. So I loaded up the female one by passing it into a function that I have in SIGSYS called FromWave, and it will return the sampling rate and the vector itself. I can then add some noise to it, which I did in here. I added some Gaussian noise to it, created another vector Y, and I can come down here and I can play it from a WAV file if I save it off to a WAV file, which is what I was doing here, to WAV. Just lets you put in the file name if you want to save it to, the sampling rate you want to save it at, and then the vector itself, the from WAV. Up here is just the opposite direction. Give it a file name, and then it returns out the sampling rate and the vector. I can play it directly, or I can play it through the WAV. Since the samples are available in the workspace, I can just do this.
Hoist the load to your left shoulder.
And I'm playing it through
Take
the audio
the winding
system.
path to reach the lake. Note closely the size.
It may sound interesting, they're reading out of a book. I don't know what the book is, but there's interesting, it's just talking. It's a test vector. We'll get into this after the break, but we're going to be doing this. We're going to be actually experimenting with what we just talked about, and we'll show that it works, and I'll show how we're going to break it very easily without having a coherent reference. So I want to have this by my side because I want to be able to jump over into this domain of my notebook, which we're about ready to take the break. But before we do that, I'll just flip up here one other thing I did. I'm in Jupyter Notebook a lot, and some of you may have noticed there's a bell down here in the lower right corner, and you might see a number inside of it. If you click on that, it will say things like this: a newer version of JupyterLab is available. I generally don't put them on every time a new one comes out, but if you click this link, it will bring up a web page and it'll tell you what the new stuff is, what patches they made and things of that sort. So if you're interested in keeping your system up to date, you can update any and everything you put in your Python virtual environment. But over here I brought up another terminal window, my Anaconda PowerShell prompt, and I just typed in conda list. So I'm just going to look down in here and see what am I running right now in my system. I'm running JupyterLab 4.5.1. So I could go ahead, and I'm not going to do it right now, but I could go down here and I could just do conda I would just do that at the command prompt, and it will go through the gyrations, kind of like when you installed it, and it will show you that it's figuring out the solution, and then it's going to give you eventually a yes or a no. Do you want to do this, or do you not want to do this? I wouldn't do this with Jupyter Lab running because it's already running, and you're going to try to, put a new version of it on your system. But if you were to do that, and I've done this on a couple of my systems, I just haven't done it on this one. I'm 3 versions behind. But if I wanted to find out what went on with Jupyter Lab, here's a list. What are the pros and cons to updating constantly? Biggest pro is you might get a feature fixed that was broken and giving you a headache. The biggest con is they might have broken something when they created a new version, and now you put that on your system, and now it's something that you really need, and it's broken. So you have a risk involved with it. I don't jump on board it immediately, but I was having problems in my last year's work where I was constantly looking for fixes, and then I ended up fixing it in another way. And I don't think I showed that to this class. I remember showing it to the DSP class last fall. Just something to think about. Like I said, I'm not going to do it. As a matter of fact, I'm going to make sure I don't accidentally do it. I already deleted it, so I can just exit out of this terminal window and not have it there. I'm currently running in these 2 windows. One of these is running Jupyter, that's this window, and this window is running Marimo notebook that we were already playing with today. Hopefully by now you're very familiar with running terminals, and are you feeling a sense of empowerment with running terminals, like you're in charge? You've got some things running. I mean, it should be like, I kind of know what I'm doing. I'm not just double-clicking an icon. I'm actually running something from the terminal, and you know how to stop it and kill it. Does everybody know what I'm talking about when it comes to killing? Okay. There's things you got to do. Okay, so let's take the break, and we'll come back, and we'll start exploring when you don't have a coherent reference, and then we'll be listening to a tone, speech, and then some binary phase shift keying applied as a message, and just see what's going on with all that stuff. So we're at 9:34. How about 9:45, 46, 47, somewhere in there? Come back, and I'm going to pause the recording. Okay, we're back from break. I think I'll just start doing it always in 2 segments because it crashes every time. What I want to do is just jump quickly over to where we're at in the lab, just so you can see the lab is starting in the same vein that we've just been going through, but it's going to go into spending time on the multiplier. What we just went through is ideal multiplication, and what we're going to continue on it in the lecture notes, but it'll start looking at some models for mixers. And this ends up being something that comes up later in the notes for Chapter 3. But in the lab, you'll be playing with the double balanced mixer serving as your multiplier. And you're going to be characterizing it and understanding how this compares with an ideal mixer. This is an electronic circuit. It's got a ring of diodes in it that are presumably matched because they're on one substrate. And then it's got some balance or transformers to couple it from single-sided 50 ohms to balanced line for driving the diodes. And the diodes are generally Schottky barrier diodes. Does that make sense to you from microelectronics? So it's a fast switching low capacitance diode. So back over here to where we're at. We're going to want to get back into here. So drop down into that. So what we're going to look at now is what happens if we don't put in nothing, but we put in as a model. And this is the electrical engineering signals and systems communications theory way, is let's hypothesize we don't know the exact frequency, we don't know the time delay, we don't know something about the signal that arrives at us, so we know we're just going to throw in a model theta of t to make an imperfect carrier reference, and then carry through the math. We now are going to work through the trig identity portion of it. So now the trig identity, and remember I said you'd be needing these, so we go over to here, go down and look at the crib sheet, which you will be having. So I offer these up that you'll have by your side taking the exam, the trig identity. So we just bounced into this one right here.
Will we have Fourier transform pairs?
Yeah, you have everything that's on this sheet.
Oh, okay.
That'll just be attached to the exam.
No, I'm asking you to print it. And if you need me to print it, I can make you copies, but remember we talked about this. I'm assuming you can make your own and just have them. But what you're saying, you want me to burn some UCCS dollars?
Might as well. I can put it up.
I pay enough tuition.
I know. I mean, I can do it. I just have to go up there and do it. I will do it two-sided to save paper, and it will be useful the rest of the semester. You will make your own two-sided crib sheet up when you take the exam. But so yeah, you'll have this stuff. If you ever watch Charlie Brown, which I know is kind of old-fashioned, but Linus and the security blanket, so this is your security blanket. I have two thin coated dogs at home, a Whippet and a Manchester Terrier, and they're covered in blankets almost all the time, and they cry to get covered with their blankets to get warm. It's kind of the way they live. But at any rate, we'll be doing this a lot. We'll be referring to these trig identities a lot, and you'll be loading them back into your brain again. So we're back over here, but we're going to stay here for right now. So we multiply it out, and this is our background now from Chapter 2 review. We look at this and we say, okay, we have the double frequency term is still getting modulated by m of t. We have some phase modulation on there now, but still this spectral notion still exists. We have a signal that maybe is getting phase modulated around by that cosine of theta of t, so it's causing some errors in here, it's causing some errors in here, but we can still use our low-pass filter to say we're going to get rid of the double frequency term, and now we'll be down into, this is coming out of our low-pass filter. So what are the ramifications of cosine of theta of t? As a simple example, and then this is what I'm going to demo to you, and you'll get to listen to it too. If theta of t was a constant, what bad thing could it do? Suppose it was hanging out at pi over 2, it would annihilate the signal, right? It would be gone, because cosine of pi over 2 would be 0. If it's slowly varying, then it would appear as an attenuation factor. Suppose it's slowly varying with some frequency, so theta actually corresponds to 2 pi delta ft, so it's a small frequency error, in which case then if we carry this through, we're going to get, for tone modulation, suppose our message was just a tone, we're going to get 2 tones that we're going to hear here at the detector. And you've seen this back in 2610, remember this way back when. This was actually studied because it was a precursor to a time like this. So this is the superposition of an upshifted and a downshifted tone. So we're going to be listening to that shortly. It's not real pleasant, and it can take the speech. So before we go do the demo part, I'm going to say what we need to be able to do with double sideband is we have to generate a coherent local reference. So we need coherency, and we need to generate it locally. So one scheme is to square the received signal, and if we square the signal, in other words, send a path of it down through a squaring operation, a narrow bandpass filter, what will happen is we will get a double frequency term here, and as long as there's some non-zero value for m squared, in other words, something is always in motion with a waveform, we'll have some power as a result of squaring the signal, and then we can divide by 2 and divide the frequency by 2 after we filter out the component, the pure carrier at double frequency, divide by 2, and then use that to get the coherent reference back by deriving it from the signal itself. So that's one technique, and this is what it would look like pictorially. We'd have a DC line component as a result of m squared of t that hopefully we could track with a phase lock loop, which we'll talk about in chapter 4, and we can do something with it. Now this is the truth of the matter is a DC component is not present in m of t unless we do it on purpose. It's just going to be like an audio signal would be fluctuating up and down. A digital non-return to zero waveform will average to 0. So we have no carrier term present. So I'm just saying, when I say read delta of f plus and minus fc is not going to be present in our received signal. So double sideband is also known as a form of as suppressed carrier modulation. There's no purposefully placed carrier. All the information is in the sidebands, upper and lower. There's no pure carrier. We're being very efficient, and that's actually the way digital comm works essentially all the time. You want to put all your power into your information. You want to let some other means obtain the carrier, and this is what's going on all the time in digital comm, where you have to get the coherent carrier back. We're going to move into in the next section, but first I'm going to demo the DSP side of it. The idea that you could put a small carrier, just add some pure carrier to the transmitted signal. So just put this gain scale of k and add that in, make k much less than 1, and then this is what you'd be receiving. It would be possible, if you could narrowband filter that, to lock a phase lock loop onto that pure carrier and then be able to demodulate as well. That's just another idea. Amplitude modulation takes us to the extreme, and this was done around in the 1900s area with AM modulation. That's when radio broadcasting came into being, and it was used by the military too. Amplitude modulation was the way to go. We'll look at that, and we'll look at what's not good about it. I mean, everything's got pros and cons, so complexity, efficiency, and things of that sort. But let's try to get some value out of this. So the first thing I'm going to do here is I'm going to create a rate-changing object so that I can upsample by 12 and get up on a higher carrier frequency. So I'm going to construct an upsample by 12, which will take me from 8 kilosamples, which is what the speech vectors are recorded at, up to 96 kilosamples per second. Let's just do something else. Suppose I wanted to play this back at 1600. This just lets you know how flexible you can be with what we can do.
Point the low to your left shoulder. Take the winding path to reach the lake.
So we can, we can speed it up and slow it down, and that's what we're going to be doing. We're going to be speeding it up by 96, but then we'll take it back down to 8,000. And so I could do that if I wanted to too.
Hoist the low to your left shoulder. Take
She
the
has a
winding
deeper
path
voice
to
now,
reach
right?
the lake. Note closely.
Just make sure you understand that.
Hoist the low to your left shoulder.
That sounds better. I've heard these too many times, so I'm used to listening to them. So now we're going to create an object, this rate change object, which we're going to rate change by 12. It has built into it a cutoff frequency of 0.9 of 800 or 8 kilohertz. And I'm using, by default, it uses an 8th order filter, and it uses a Butterworth filter. So I'm just going to go with the flow there, but I am going to take the filter order up higher. So I'm using a 12th order filter. So objects created, and now if I go up here, I can just see what are the methods that I have that go along with this instance. So I hit dot and hit tab, and I can see there's a bunch of attributes that are stored inside that I can upsample and downsample is mainly what we're interested in doing at this point with this object. It's just going to be a tool to do the signal processing. So I'm going to define a 10-second span to listen to. I'm going to eventually switch in some non-return to zero PN data bits running at 8 hertz per second. Let's see, what do I have here? Yeah, I'm going to put 8 samples per bit in. So at 8 kilosamples per second creation rate, I'm going to be at 1/8 of that. So I'm going to be at 1 kilobit per second for my digital data when I use this later on. But initially, I'm just going to put up a tone at 1000 hertz and take that all the way through the system, look at the transmit spectrum, and then we'll look at the coherent demodulator all the way through. And then I'll comment that out, put in the speech vector, and then I'll put in, as another alternative, digital data. I guess I have it as 100 bits per second. I was still thinking it's going to be a kilobit per second. Doesn't really matter. The idea is it's bits rather than speech. So I'll run this. And what did I not do? I didn't run this line of code here. So there's just seeing what the filter looks like that was designed. There's a method in there to actually get the frequency response of the filter. So there's the filter rolling off. Just to give you an idea, because it's going to roll off, but it's going to have some artifacts that come through from the upsampling. It's not going to be a perfect upsample. So now I can run this. And there it is. I've upsampled it. So now this is at 96 kilosamples. So this is stopping at 48, which is the folding frequency. This is my message at 1 kilohertz. You can see that this is just leakage because the filter is not rolling off perfectly. And just to give you a flavor for what I could do, I could take this up to, say, 15, and now my filter is rolling off faster. And now the leakage is suppressed. But this just adds more complexity because it takes longer to filter it. I'm willing to just let it be not quite so perfect. So I'll put it back at 12, 12th order filter. And run this again. So there's our signal. Now what we're going to do is we're going to modulate it with carrier, modulate it onto a carrier. And the first thing we're going to do is, this just lets you know that there's the 1 kilohertz. Now we're going to modulate it on a carrier that's at 24 kilohertz. It fits within our 0 to 48. It sits halfway in the usable band when sampling at 96 kilosamples per second. We're going to upsample. So the time axis for upsampling is T up. And now I'm going to multiply the upsampled message, which was created down here. I created the upsampled version of the message, and this was the spectrum of it we were already seeing. Now I'm going to multiply that times the carrier, and then I'm going to plot the spectrum in the time domain waveform. So we saw this in the notes. This is the transmitted signal. Carriers filling in between at 24 kilohertz. understand in reality this is going to be gigahertz or megahertz. I mean, this is just for easy modeling on the computer. And we're seeing our single tone is producing an upper sideband that's 1 kilohertz above 24 in the lower sideband. And do you see a carrier there? Remember I said suppressed carrier. It's not there. And you will be, in the lab, you'll be kind of studying this because it won't be perfect. You'll see something, but it won't be as perfect as this because we're doing an ideal multiply. But this looks like the envelope picture. And now we can coherently demodulate it. We're going to coherently demodulate it by multiplying by 2 times the original carrier. So this is the modulated carrier XC, and now we're going to multiply by a coherent carrier. It's exactly at 2400. Carry this through, and these were like the pictures we were looking at in the notes. The upper one there is just the shifted down to DC, and then at double frequency, remember the picture where it was, the envelope wasn't two-sided anymore. And then we're seeing back down here at 1 kilohertz, and then here's shifted up 1 kilohertz from 48. That's that guy right there. Is that making sense? Those are all our spectral lines for, and hopefully now you're understanding why did we do all this stuff over the past weeks. It's because we're just trying to develop this second nature to looking at spectra. So now we'll recover the message. We'll downsample, and that has a filter built into it already. So we're going to downsample. Well, actually, never mind. We're going to low-pass filter using, let's see. Yeah, we're using an FI. We're using the filter coefficients that were in the upsampler. A B vector and an A vector is coming out of there. So we're going to low-pass filter to recover just this piece down here. And there's our 1 kilohertz back, and there's our spectrum. And then here I can just listen to it. Sorry, it's a little bit loud. Do this at home and it'll drive your family crazy. My wife does not like hearing any of this stuff at home. Okay, so now we're convinced that that works. Now, let's just add some realism to it. Now let's put in let's uncomment the female speech. And it's occupying a bandwidth of about up to 4 kilohertz. Because it's 8 kilosamples per second, it's going to be, up to the folding frequency. And now we put that on the carrier, and it's a lot weaker looking, so I could boost the gain up. I'm just going to leave it down here. This is the modulated double sideband signal, and then this is just a snippet of the speech. It'd kind of be having this speech appearance to it, opening and closing. That's just part of a syllable or so in the speech. And now we'll come along and coherently demodulate it. And there it is, the speech back at baseband, and then the double frequency. And then we'll recover it with the low-pass filter again. That's the speech coming back. That's the spectrum of the speech and some of the leakage from the filter.
To your left shoulder. Take the winding path to reach the lake. Note closely the size of the gas tank.
It works, right? You're probably saying, it's so simple, it has to work. Well, we're going to mess it up. So now I'm going to send through the digital. I'm not going to always spend this much time, but I just want to do this at least once here. You will probably do things like this in a project, but we're going to put in the digital at this point. And did I get this right? No, I didn't change it. I didn't change the right thing. The spectrum definitely didn't look like non-return to zero spectrum. There it is. So what we're seeing here is we're seeing the humps of the NRZ data right in here, but then this droop or fall off is just because we're filtering with a low-pass filter before we go into the modulator. So that's just the filtering action of the upsampling. As long as we get a few lobes in, we have a high quality or good enough quality waveform. We just have to get rid of some of the side lobes because they don't fall off that rapidly. And if I wanted to listen to it, it just sounds like a chopping sound, kind of maybe like a noisy helicopter or something, a blade or something. At any rate, carry on here. What we're seeing here is we're seeing our PN spectrum. This would be binary phase shift keying sitting up here at 24 kilohertz. The sidebands, again, are rolling off faster because we have the upsampling filter. These are individual bits, and we have the transient response of the Butterworth filter, making that we have a burst of carrier at one phase, and then when the bits change polarity, it will be a burst of carrier at another phase. This is probably a single one, and this maybe is a string of zeros or vice versa. So we're just seeing how the carrier is getting phase shifted because we're multiplying by the NRZ, which is the plus or minus 1 type waveform. So now we'll go ahead and demodulate it. Again, it's got the impulse response of the filter, so it's not looking like super great at this point. And if I low pass filter it, it doesn't look like it has perfect edges, but it still looks like ones and zeros in that NRZ waveform. Agreed? Okay, so now this is where I'm going to blow things up a little bit. We can listen to that again. Sounds a little bit different because of the higher frequency, I guess, because of the ringing that's on here. But now what I'm going to do, suppose we don't demodulate by 2400, we just shift it by 20 hertz. We're off by 20 hertz. Spectrum looks good. The waveform looks good, but it's not entirely clear what's going on. But now we look at the demodulated waveform, and what that 20 hertz of frequency error is doing is it's chopping through the waveform, and it's scrambling it. It's flipping the polarity of the bits. It's putting in a time varying attenuation. It's gone. I mean, we don't have data bits anymore because the polarity is changing on them. We're not tracking and using a coherent carrier. What does it sound like? I don't really remember anymore. It doesn't sound that much different, but so this is significant to me. I mean, what do you think? Without the coherent carrier, data bits can't get them. We have to be tracking the carrier because even at a 20 hertz error. So now let's just quickly go on with the speech. How does the speech survive when we do this? So I'm going to go take that one out, put this one back in. Unfortunately, I have to take it all the way through all of the steps. So now we're demodulating with a 20 hertz shift. The spectrum again looks kind of reasonable, but if we try to come back and play it back, here's what we're going to be hearing. We're going to be hearing a 20 hertz shift of the message signal up and down superimposed. So we're going to hear two voice spectra that are shifted up and shifted down, overlapping.
To your left shoulder. Take the winding path to reach the lake. Note closely the size of the gas tank.
You hear that? Can you sense that? It's like, it just doesn't sound right. But
left shoulder.
Our brains are amazing, right? Our brain can still understand that and figure that out, whereas our digital modulation scheme is hopelessly not able to do it. What does that say? Our brains are powerful. I think AI, what did I see last week? We need less stupidity or something like that. We don't need AI. We just need people that to be less stupid or something. I don't know. It was some, I'm not saying it right, but people are making a lot of interesting stories or interesting comments. So that's kind of why we need a coherent carrier. So the next answer to this, though, is amplitude modulation. How can we design a transmitted waveform that we can put more of the burden on the transmitter and less burden on the receiver? Because that's how radio got started. The transmitter was sophisticated. It was had a lot of power it could send. The receiver was going to be in the hands of, say, the consumer way back when, and they wanted to have a low-cost receiver. They wanted to be able to listen to the wireless or listen to the radio and so on. So we use AM modulation, which is coherent modulation. I mean, is double sideband modulation, but now we're going to add in a constant A. So we're going to be multiplying our carrier times a biased version of the message. And this is just another way the book writes things out. This will be in the homework problems eventually that you'll be working on, but we have still an overall AC that we had before, but now we've got effectively a 1 plus A times MN, and A is called the modulation index, and MN is the normalized message, again, the way the book likes to define it, so that the message never swings below -1. And then that allows A to control the depth. So this is what the waveform looks like as a result of that setup. We see the envelope again, but the envelope is never crossing itself. That's notable, especially in here. You don't see the envelope sort of crossing through like we saw with double sideband. And what that means is that we can recover the information from this with a simple envelope detector. It's because the envelope doesn't cross as long as the modulation index is less than 1. So at the receiver, and this is just the generation of the AM, adding a bias and then multiplying and so on. I'll probably think about this maybe next week, say more about it, because you'll be dealing with this in some of the homework problems for sure. This is what the envelope detector looks like in the analog era of being just simply a diode and a capacitor and a resistor. So it's a nonlinear circuit that has RC in it, but the idea is that you're going to rectify or half-wave rectify the signal so you get back what we see here, just the positive extremes, and then you're going to try to remove the carrier that's still embedded inside of this with the RC filtering action. And here's an example that I did in SPICE a long time ago, but it's a SPICE simulator that I had. And you're just seeing by adjusting the capacitance or the R value, you can get pretty good recovery. The little bit of carrier that's leaking in here really doesn't, first off, it's not going to be audible because it's going to be at a high frequency. Your ears won't be able to hear it. But you don't want to be sending a lot of the RF into the amplifier and trying to amplify it or just overloading the amplifier. So you will have some filtering action there. In DSP, let me just jump back over here. I showed you this weeks ago, but it was the project for modern DSP, Project 2. The channelizer, this was AM radio. It was all channelizing DSP, done in DSP, but what did the AM detector look like there? It was taking the absolute value of a complex baseband waveform and then DC blocking it. So in our envelope detector in the analog domain, what we were just looking at up here is we do this, but even when we put the filtering action in, it's riding on a pedestal. So we still have to put in a coupling capacitor on the output to get it centered back on 0 if we're doing, like playing this out as an audio, as an analog audio. I have all of that set up in over here in the Jupiter, I'm not sure I want to go through all the gyrations over here, but I do have the amplitude modulation set up in the notebook, upsample. This is the analog message. Let's just look at, which one do you want to look at? I don't really want to look at the PN, although that works. Do you want to look at just the sinusoid, or do you want to look at this female speech? Actually, I think on this one I might have used male speech. I guess I didn't. Do you have a preference? The tone? Speech, okay. Speech is more fun, right? So there's just a cliplet of the speech. I'm going to generate the AM by upsampling, and I'm adding in a normalization, and I'm setting the modulation index at 0.8. So now we see that it's filled in, but it's not crossing. So we can visualize, we can clip this upper half off, then we can eventually remove the carrier component in there. So what do we see that we're going to see back in the math side in the notes is that we see this large spike. We've added in a lot of pure carrier. The transmitter is doing this. In the beginning of AM radio, they just put a lot of power into that pure carrier. It's a waste of power in the sense that it doesn't contain audio information or message information, but it allows the signal to be easily demodulated. So does that sound believable? I mean, think of something in a consumer sense, and I'm just popped in my head, where something is done to make it low cost for the consumer, but it's very inefficient. Like, I don't know, maybe I'll use an example, packaging. Packaging gets something to your house from Amazon, but it has a lot of wasteful material around it. So they've been efficient, making that more efficient, but styrofoam is definitely not a great thing to send something in because disposing of it is hard. So that's an engineering decision, though, that's made all over the place. That's where the term sustainability comes from. And an AM radio has got a sustainability problem. AI has a sustainability problem because of all the power that has to drive the server farms.
So just make the center frequency really high so you can modulate it easier? You can find it and modulate it easier?
It's really high because we want to carry it at a frequency that we can get an FCC allocation at. This is just a model. We would shift this up to a much higher frequency. But it's the pure carrier that's sitting in here that expanding it so we can detect it with the envelope detector very inexpensively. Pocket radio is what I'm thinking of. So demodulate the AM. All I'm going to do to it is get the envelope back again, and what did I do here? Half-wave rectify it with a simple envelope operation. That's what this thing is right here. It's just a nonlinearity. And then I have to low-pass filter it, and then I have to DC block it. So here I low-pass filtered it, and then I'll DC block it. I'm not even sure how I did that anymore. Still not DC blocked. I don't think I got rid of the DC because of the fact that it doesn't pass through this system in the audio. But it worked, right? I mean, it definitely works. You guys are too young to think of having an AM radio, but when I was growing up, having an AM radio that you could go anywhere and listen to sports or whatever, talk radio or music, it was just, you know, my mother listened to the AM radio all the time for music and stuff. This was the beginning of radio. So getting back over to here, what we'll look at is easy demodulators for AM, but what's the downside? There's lots of power that goes into the transmitter to transmit just pure carrier. And that's something that the homework problems look at. And we look at, if you analyze the waveform, you look at what is the total power in our transmitted signal, and then you work with this model for the transmitted signal, and we have to square everything, so it gets messy. That's why the second line here has got cross terms and things in it. We're going to even assume that the message has got an average value of 0. That will simplify things somewhat. But what it comes down to then is we have these two groupings of power that's in the carrier, AC squared over 2, and the power that's in the normalized message, also scaled by A squared, the modulation index, AC squared, and divided by 2 as well. And then the book defines AM efficiency as what is the ratio of the power that's into the message and the total power that's being sent. And it's deplorable is what it is. Suppose you were going to transmit a kilowatt out of a transmitter at a modulation index of 0.8. It comes down in the end here to being 24% efficient. I mean, and a lot of power is just in the carrier, 757 watts and 242 watts of power are in the sidebands, which contain our message signal. I mean, we have AM radio stations here in Colorado Springs, out east of town. I can't think where they are, but if you live more east and south, I think there's a few antenna arrays. How can you tell an AM radio station? They generally have a number of towers that are spaced in a linear array. And why did they do that? It's because they form an array pattern, and they want to have it has to be away from people and not be an eyesore, but they can form a beam, so they can make the beam be directionalized into Colorado Springs and not just broadcast everywhere. That's a typical AM radio setup. And it's vertical monopoles, and they'd be dipoles if you reflect them into the ground, and then you can do an array factor. And take Dr. Song's antenna class. I'm pretty sure she talks about, she did, right? Yeah. So there's more things to do in this. What am I not saying that I want to do? I've got 10 minutes left, so I want to think, what else do I want to talk about? Does anybody have any questions so far? These calculations are going to be a little bit nitty-gritty, and you'll have to get into it. But I don't want to spend an infinite amount of time on it. Probably the biggest thing is what I've already said. Double sideband is very closely related to the evolution of digital comms techniques, but it requires the coherent carrier. On the AM side, we can use this for digital as well. It's actually used in modulation in remote controls as well, maybe for an RC car or a TV remote, which is probably optical, but the AM concept is spread around in different modes of devices that we still use to this day, but for broadcasting, it's not very efficient, but it puts all the simplicity in the hands of the consumer, so that's how it's justified, I believe. For things like remote controls and other things that might be used, radio RC controls and things, they might use a form of AM there. Again, because I'm thinking now of a drone and other things, how do you want to make the receiver? You want to make it simple still, because it's low cost, it's going to fly in a drone, it can't take up a lot of weight, so you get to use AM modulation. It just means that your transmitter is going to use more power just to get the signal up there and allow for a simple receiver. So what does anybody think about that? This has been our life for over 100 years now. And AM radio was the beginning. FM radio we'll look at in the next chapter, but I'm going to have you study more on digital modulation too. So this was one example that I went through. What about a pulse train? It's obviously getting exciting out there because we're getting people going out of class and talking loudly. Thank you for closing the door up. This doesn't look like a very interesting signal, but in an attempt to understand how we could get more efficiency, suppose we were going to send a pulse train and we just wanted to see how effective we could get a pulse train sent through with AM modulation. And this could be thought of as a form of digital modulation at that, where we would put a bias on it, or in this case, the duty cycle of the pulse train gives it a bias automatically. So we go through this analysis, which I did in all the detail that was needed to get this calculation completed, the time average of the normalized message. We find out that for this waveform we can get up to 67%. If we were to go down to, let's see, an inverted version of this waveform, we can become more efficient or less efficient, just 33%. And if you go to a 50% square wave, 50% duty cycle square wave, with 100% modulation index, you can get still only 50% efficiency out of AM. But like I said, it can be used, and it can allow you to have a low-cost receiver. You don't have to have a coherent carrier. You're always transmitting some carrier, and you can just envelope detect it and detect the ones and the zeros without having to have a coherent carrier. I think there's some problems that look at, suppose you had a multi-tone signal, or you just had any signal. How are you going to make sure that the modulation index the waveform can be normalized and the modulation index never goes over 100%? What I did not show you here, but I want to go back since we're closer to being done. What happens if I drive this modulation index up to 100%? We didn't really talk about that picture-wise. In this case, I'm obviously not scaling it because I'm using the audio, so let's go back and generate it with just the sinusoid. I didn't have a good capture, a good calibration on the audio. So that's swinging between plus and minus 1. This is what's called 100% modulation, and you'll be seeing this in the lab. So it's just touching. It's just closing up enough that it's touching and then going back up again. If you think of using the old-fashioned diode envelope detector, it will have a turn-on voltage, and it won't be able to capture that valley right down to 0. It will get clipped away, and it will cause distortion, clipping in the received signal. You could go with a Schottky barrier diode, which would have a 0.2 turn-on voltage, and then that would do better. Or what I have shown in the lab, and I hope Geronth has you look at this. What you do later on in the lab when you're demodulating is you will be looking at a model and then implement it. Getting way down here in the details of this. There's the basic envelope detector, but this is a circuit that used to be called a superdiode. That was the name of it, where you can put an ordinary 1N4148 silicon diode in a feedback loop of an op-amp and use the gain of the op-amp, and you can effectively make this look like an ideal diode. So you can take the modulation index down up to 100% and still be able to rectify and not get any clipping. And this does that. DSP can do this more effectively because it's an algorithm, so it doesn't have the limitations of the diode itself because it's doing it with an algorithm. But those are things that can definitely be done to make life easier. But those of you taking the lab will be exposed to this, and what you're going to see is a general rule is that you don't want to let this happen because you'll be you'll definitely have problems recovering it. And if you're going to look at it on the scope, like if I just increase this by 0.1, you can see it's now crossing through, and it will not, you can't recover the message completely with this. It will get clipped. And if I go down here to demodulate it, it's not going to look correct anymore. It's kind of nebulous seeing that, but it's starting to get a distorted look down there because it's getting clipped by the action. And this is a perfect diode still in the model here. This is a perfect clipper. So what are we going to go on to next in the lecture? We'll look at multiple sinusoids and finding out what the minimum is so we can scale it properly. That'll be probably in a homework problem, I'm guessing. But then we'll start looking at single sideband modulation, and what single sideband modulation was created for was to be more efficient. And it was used in a lot of different locations in applications. The idea with single sideband is when we modulate double sideband, we have the upper and lower sidebands, and they contain the same information. So what people wanted to be able to do was transmit just the upper or the lower, and that way you could pack signals closer together because you'd be more bandwidth efficient. And the telephone company, when we were using analog lines to put out each individual household into the network, it was actually carried over the analog lines as single sideband. So if you had 100 channels, you could pack them into a bandwidth of, say, 4 kilohertz times 100, because all the 4 kilohertz audio could be just right next to itself. And that was what single sideband offered up. Amateur radio people use it. When TV came along, and color TV, and then digital TV came along, they all recognized the same fact that double sideband was just taking up too much bandwidth. So they came up with a way of using less, and that's where vestigial sideband came in, where you would transmit only a portion of one of the sidebands, but you could more efficiently do that than the full single sideband could. So to talk about single sideband, we'll have to talk about the Hilbert transform, and I do want to talk about it some. I want to show you some of the things. I have demos in the notebook with all the audio listening that we've just gone through with the single sideband. I designed the Hilbert transforming filter. It's just more, in my mind, it's more on the fringes. It's not on the mainstream digital comm that we use for cell phones, networking, video all over the planet, doing cable TV, fiber optic, et cetera, et cetera. But it is on the fringes. It's used in, like I said, in HD TV broadcasting uses a form of vestigial. And why do some of these things keep happening? I think what it is as a community, we look at legacy, and what do we do? What are we going to do? Throw everything away and just not use it anymore? TV was a big, huge change when it went to digital. Everything had to be discarded, and we had to come up with a new scheme. And the government went down that path and got ready to do it, and the makers and the technology groups that came together with a standard, all the TV stations around the country, they got ready to start, and then they said, nope, we're not ready yet. We just don't have everybody on board. We're going to leave people without anything. And then this happened in your lifetime, I think, right? I'm pretty sure it did. What did you do? You ended up having a TV at home that maybe you had a box that could still convert a digital to analog format that you rented from the cable company or you bought something. But eventually the changeover happened. It happened on one evening. Maybe it was the turn of the year. I don't remember anymore now. But it eventually happened. And then everything's old is gone and the new had to come in. So when they came up with technologies and innovated things, they still had to be thinking how can we produce TV sets that are low cost and put the burden more on the transmitter, because that's the same with TV broadcasting as radio broadcasting. So there's just a lot of different things that had to happen. And inside our government and military stuff, we still have, I'll say, pun intended, vestiges of the past are still present for legacy stuff, which I think is just the way it always will have to be, because it's so hard to just, well, it's like what I'm doing at home, cleaning out the entire house so they can take over the house. It's so hard to clean everything up and start over from scratch. We're not, in the house, we're not starting over from scratch, we're just putting it in storage. But I was doing cable TV at the time, so I think all we had to do was buy a new TV, but if you were doing over the air, you had no choice. You had to buy a new TV as well, and it was a major deal. I'm going to stop at this point. Are there any additional questions? We've already decided exam will be 2 weeks from today. We'll talk about it next week, but for sure look at the old quizzes, be looking at the old exams. I will be going through some of that stuff next week. My plan right now as I close out today is to say that we'll just make this exam stop with Chapter 2, and I'll tell you what we're expecting there. So when you look at the old exams, you will see problems from the first part of Chapter 3. We're not going to do it that way this time around. So that's good and bad. That means I can ask more questions on things that maybe is nitty-gritty, and less stuff on AM, which is, in double sideband, which is pretty simplistic in the beginning. But I'm drawing the line there. Unless you want to vote the other way, I don't think you do. We'll just keep it clean like that. But remember that when you're looking at the exams. Okay, I'm going to sign off.